Okay, good. Shall we start? Welcome back. Let's resume the second lecture from Koenraad. So over to you, Koenraad. You can start.
Thank you, Yunsik. Okay, so everybody rejuvenated and awake again. In the first lecture, we discussed all the various ingredients, and we ended with this GKPW rule, Gubser-Klebanov-Polyakov-Witten rule, which shows you how to relate the generating function of correlation functions in a CFT, the partition function, in other words, with the path integral for an anti-de Sitter gravity or string theory. And the identification is through the fact that the source for the operator O is equated with the boundary value of a corresponding field in ADS, where with the ADS boundary, we strictly mean this conformal boundary that you can see in the cylinder-like coordinates that cover global ADS. And what we're now going to do in this second lecture in quite some detail is use this GKPW rule to compute correlation functions from the ADS perspective. So we're not going to compute them directly. We already reviewed that they're basically completely determined to lowest order by the symmetries, but we're going to show how they are related, how they're computed from the ADS perspective. So that is the coming hour, hour and a half. Now, before I do that and take you through this calculation, there's one thing that in the early days of computing correlations became clear rather rapidly, but has taken on a life on its own and is very important to realize and also to read the current literature, because it's often implicitly referred to the following statement. And this is known as the UVIR correspondence. Now, recall in Poincaré coordinates, ADS looks as follows, where Z is infinity, is the interior, and Z is 0 is the boundary, but that's at an infinite distance away. And we've also shown that in this ADS metric, you can already implicitly see the invariance under scale transformations. If I take all my coordinates x, y, and t and transform into new coordinates, which are lambda times the old coordinates, right? Then what happens if lambda is smaller, right? Then I actually zoom out and I look at larger scales. I zoom out from the UV to the IR. I start with my x, I multiply by a small number. That means I'm only looking at larger scales, right? However, notice that because Z is 0 is the boundary and Z infinity is an interior, if I would do the same for Z as I multiply by Z, what I do is I look more towards the larger values of Z and less towards the smaller values of Z. So actually, I'm therefore zooming in from the boundary towards the interior. Okay, so as I on the boundary zoom out from the UV to the IR, in the bulk, actually in the radial direction of ADS, which is called in the bulk, it seems I am precisely moving away from the boundary towards the interior. In other words, smaller scales in the radial direction of ADS, where corresponds to larger scales on the ADS boundary, and vice versa. And this is almost paradoxical, or it's flipping things around. And that is exactly what is meant by the UVIR correspondence, because small scales in the radial direction, right, that corresponds to the UV in the radii direction. That means that you're going towards the interior, right? If you think of the boundary as infinitely far away, so that's the IR. So if you go to smaller scales, that means you're going towards the UV. But that actually corresponds to going to larger scales in the boundary by this transformation, right? And vice versa. If you go to larger scales in the radial direction, right, you go to smaller scales on the boundary. The more you go towards the boundary of ADS, the more you actually zoom in on the UV in the boundary. And this is the mathematical coordinate language. What that really means, thanks to ADS-CFT, that this translates in that if you probe the physics, the UV CFT physics, right, that actually means you're probing the dynamics near the ADS boundary, right? And whereas if you probe the CFT IR physics, that means probing the deep ADS interior. And what I really mean by that is that sort of the dynamics, right, that can depend on whether you're close to the boundary or interior. In a strict CFT, there's no scale, so it's hard to see. But later, especially tomorrow and on Wednesday, we will see that you can actually, once you put in a reference scale, you can distinguish between strict UV scales and strict IR scales. But you already see it in this manifestation of the Poincare coordinates. And this is known as the UVIR correspondence. The fact that the UV in the boundary corresponds to the IR in the bulk, and that the IR in the boundary corresponds to the UV in the bulk. And as we go along, you will see this UVIR correspondence show up in various points. And that is why I highlight it right now. Okay, so let's now go back to what I announced we were going to do. Let us compute a correlation function in a CFT using the GKPW rule and the ADS-CFT correspondence. Now let's take the simplest such operator. Let's take a scalar operator. And then by the GKPW rule, it should correspond to a scalar field in ADS. And scalar fields in a curved space-time that we know very well, right? This has the following action. And notice that I'm right now working in ADS D+1. So my CFT lives in D dimensions. And well, because ADS has this one extra radial direction, the direction orthogonal to the boundary. And the equations of motion for this are just the following equation. We're working in a curved space-time. So we have this curved Laplacian with various determinants of the metric G and the inverse metric G. And if I substitute in, or when I substitute in this Poincare metric, and you will see also this here and a lot in the future, this Poincare metric is just easier to work with than the global coordinates. Moreover, in the Poincare metric, the boundary is flat space, whereas in global coordinates, the boundary is a sphere. And this has a difference. For instance, in the question that was asked right before the break about the anomaly in a CFT, and on the sphere, the CFT cannot have an anomaly, whereas on flat space, it does not. So in the Poincare metric, all right, you need not worry about these things. So I'm going to substitute the Poincare metric in here, and it's rather easy to see that, for instance, this is di squared. This is the derivative with respect to the directions xi and t, and z is the direct derivative in the radial direction. And this overall z squared just comes from the inverse metric g mu nu here. The factors of z here cancel in between, but because d mu can include a dz, there's one term. There's now a first order derivative term where this dz acts on the z components here. And it does so with a power d minus 1. And this is what you get out. And then the final term is an m squared r squared. And this r squared also comes from the fact that g mu nu invert goes as z squared divided by r squared, and I've multiplied the r squared all the way through. So this is a one-line derivation to construct this differential equation. Now this looks like a simple differential equation, but for those of you who are extremely astute, you may actually immediately recognize this differential equation. This is a Bessel equation. And Bessel equations you also know from electrostatics. Anytime in electrostatics you had to solve a cylinder problem, right? For instance, a point charge in a cylinder with conducting walls, or objects like that, right? Or a coaxial cable, you find out that the corresponding field equation is a sort of an equation for the electrostatic potential is a Bessel equation. And that's exactly the same here. Because topologically this system looks like a cylinder, you get effectively a Bessel equation out. It just is a reflection of the cylinder symmetry in the problem. So we can solve this equation in principle exactly. Now, when we go to later more complicated problems of ADS, where it's not pure ADS, but sort of we put more things into the space-time and it's only asymptotically ADS, then we cannot solve it exactly anymore, and we need to solve it numerically. And therefore, what I'm going to describe is I'm not going to describe the exact Bessel function solution, although that is very useful, and then you can reproduce all the exact CFT correlation functions. What I'm going to describe to you here is how to treat equations like this in general, which also applies to spacetimes that are not exactly ADS or not exactly in Poincare coordinates. So to do that, let's focus on the near boundary behavior, the region in Poincare coordinates where z is very, very small. Okay, in that case, when z is very, very small, I may ignore this di squared, right, term, and the equation just reduces to the following term plus dot, dot, dot. Now, this is a second order differential equation. It has two independent solutions, which are characterized by different scaling behaviors near the boundary, or different scaling behaviors in the regime where z is very, very small. And you can extract these two different scaling behaviors by simply substituting in a power law ansatz. In other words, you assume that phi near z is 0, behaves as z to some power plus dot, 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 dot. So let's substitute that in. Let's substitute in z to the power delta into this equation. Here I have two derivatives, so I get a delta and a delta minus 1, z to the delta minus 2. Here I have a single derivative, so I get one factor of delta. And here I had no derivative, so I just get z to the delta is 0. Now the overall z to the delta scales out, because here I have a z squared, here I have a z delta minus 2, here I have a z, here I have a z delta minus 1. So all these objects scale as z to the delta, so I can divide it out. And I'm left over with my characteristic equation for the boundary behavior of this differential equation, which is now characterized in terms of this to be determined exponent delta. Now, this is a quadratic equation, right? And which has the following two solutions. Delta is d over 2 plus or minus the square root of d squared over 4 plus m squared r squared. So these are the two delta where you choose a plus and delta where you choose a minus are the two independent scaling behaviors that are consistent with this differential equation near the boundary. And because they're different exponents, they characterize the two different independent solutions to the equation in motion. Now, as a small preview, I don't do it here, but we will later see that delta turns out to be the scaling dimension of the scalar CFT operator dual to phi. And that's why the notation delta has already been used. This is the same delta that I reviewed in the small review of CFT a moment ago. Okay, so this means, as I mentioned, that phi has the following asymptotic, the general solution equation of the following type. There's the asymptotic behavior near z 0, which either goes as z to the delta minus, where I chose the minus in the square root, and then there's 1 plus higher order terms in z, or plus b, z to the delta plus, and 1 plus higher order terms in z. And the a and b itself can still depend on the other coordinates in the system and xi. Now remember that this delta minus, right, is of the following type. So in particular, if the mass is very, very large, delta is negative. This delta minus is a negative number. So as z goes to 0, this goes as 1 over z to some power. So this diverges. So this is the most divergent term. In other words, this is the one that survives near the boundary. And there's the first step that we need to use in our construction. Remember, the GKPW told us that the boundary value of phi should be identified with the source term. So this coefficient A, that's the most divergent term. That's the term that survives at the boundary. So that is the one that we should equate with the source J in the CFT. And that's consistent with this statement because D plus is always a positive term, right? It's D over 2 plus a square root, which is positive. And so this term always dies near the boundary, right? So therefore, this term cannot be set equal to the torus, right? Now, it still characterizes an independent solution, but because this dies near the boundary, it's hard, or you have to take several derivatives to set it, to set the boundary condition at the boundary. In fact, the ADS-CFT prescription tells you that B in ADS-CFT is not determined by a boundary condition at the boundary at all. On the contrary, it's set by a boundary condition in the interior, which is very easy to see in the case of pure ADS, what we are discussing here. Remember that ADS is topologically equivalent to a cylinder, and the point Z is infinity, that's the deep interior, very far away from here, is the center of the cylinder, but that's actually not a special point at all. Even though Z is infinity and things looks like they diverge, right? In principle, I can choose different coordinates and can continue right through the center of my cylinder. It's like the center of polar coordinates. There's nothing special happening at Z is infinity. So therefore, regularity in pure ADS demands that the derivative of this function at the origin, right, must vanish. The function must be continuous. And that is in pure ADS, the boundary condition that you must impose. Once we get into more complicated systems, we will see, particularly tomorrow and later, that under different circumstances, you have to choose different boundary conditions in the interior. But it's always true that this second boundary condition comes from the interior in ADS and not from the boundary itself. So one of them is, so it is a, in terms of the mathematical theory of differential equations, it's a differential equation which has one boundary condition set at one end and one boundary condition set at the other end. Okay, so now we are ready to compute a correlation function with the GKPW. So now on the right-hand side, you see the path integral over fields phi in ADS. And here we do the usual thing that we're going to do that we do always in quantum field theory. We approximate the path integral by its saddle point. Or in other words, we solve for the equations of motion and we substitute the solution to the equations of motion back into the action of ADS. And that is the leading contribution to this path integral. So that is what we're going to do. We're going to find the equation of motion given this boundary condition, substitute back into the action, and then I have what should be equal to my functional for CFT correlation function in the presence of sources. So to compute the correlation function, we're going to substitute the solution into the action. Now let's write the action as follows. Let's do one integration by parts. Then what I get is the following action. I get phi box minus m squared phi minus a half. And here is a second term, which this is a boundary term where I've written it specifically in a very general way, in the way you would learn in general relativity, where you have an arbitrary coordinate system. And this boundary itself can also have an arbitrary coordinate system. And HEB is the determinant of the induced metric on the boundary once you have a coordinate system in the bulk. So psi are the local coordinates on the boundary, and the local coordinates on the boundary, its metric is not independent, but it's related to the metric in the bulk in this way. And in very simple natural Poincare coordinates, where the boundary coordinates x are the same as the bulk coordinates x, and the boundary coordinate t is the same as the bulk coordinate t, then you get that the square root of this induced metric is z to the minus d, and this is the normal derivative. This is the derivative in the direction normal to the boundary is just z dz. Okay, but again, if you have a different coordinate system, then you have to recompute this and you can fill this in. Now, under normal circumstances in quantum field theory, we ignore this boundary term. Officially, it's always there. But that's because in normal field theory, we always consider wave functions that vanish at infinity. That is a secret assumption that is sometimes stated, more often forgotten, but it's always implicit when you do standard ordinary quantum field theory in flat Minkowski space-time, that you nevertheless have wave functions that die off sufficiently fast at infinity. And with sufficiently fast is precisely meant the fact that I can ignore the boundary terms in this system. They anyway do not contribute to the equations of motion, but to physical observables they can contribute. ADS-CFT is different in that part, that the boundary term is very important. And we all already saw that by the fact that the boundary value of A generically diverges. So it does not obey this statement that it dies off at infinity. And the second reason why it contributes, and that's even probably more intuitive, more easy to understand, is the fact that we're going to evaluate the action on shell. And on shell means that I solve for the equation of motion, but the bulk is precisely after you integrate, is precisely proportional to the equation of motion, right? So when I substitute here the equation of motion, this term is going to vanish. And the only term that is left over is this term on the boundary of ADS. So here you see, not for the first time and not for the last time, how important this conformal boundary in ADS is in the ADS-CFT correspondence. It's firstly, we've already seen that it's the region where kind of conformal symmetries, those of the CFT, become inherited from the isometries in ADS. And here you actually see that once the leading term, the leading contribution to the GKPW construction of the generating function of the correlation function in the CFT also comes from directly from the boundary of that conformal boundary of ADS. Okay. So in the previous slide, we show what this solution looked like. The solution looks like A, and here I have Fourier transform the other components times C to the delta minus plus B times D to the delta plus. And because I'm now going to substitute it in, this term vanishes and I'm only going to focus on the boundary, I can ignore all the dot terms. I really can only take these two terms. Now, what do I get? If I simply substitute that in and I look at the leading terms, there are two leading terms. One is where both...
Sorry, I have a question. So can you go back to the one slide back? Yeah. In equation 4.11, should we have to worry about the log behavior for the case when delta plus minus delta minus is integer case, for instance?
Is integer?
Yes. For the case when the delta plus minus delta minus is an integer,
when delta plus and delta minus are integer, or when they are, you can even have situations where they happen to be equal, right?
Right.
Yes, this is very well known. Integer is usually okay, but if they're equal, what you secretly happen is that you get one, then it looks like you don't have two independent contributions, right? But then it turns out you can go to your theory of differential equations, and then one will go as Z and the other will go as Z log Z. And if you do that very carefully, you can check that out.
I see.
Okay. But the easy way is actually to, it's a little bit easier to understand if they're not integer, but for the special case of integer and non-integer. If they're integer and differ by an integer, that's not really a big issue. But if they're equal, that is a special case, and that is actually an important special case that comes up several times. But then it just becomes Z and log Z. Those are the two independent solutions.
Okay.
Okay.
Yep.
Yeah. So I simply substitute this in. Remember, and I have phi, and once the derivative with respect to Z of phi, that I substitute in. So if I substitute the leading part twice, I get an A squared. The exponent was delta minus, so I get a delta minus, and I had to take one derivative, so it's Z to the delta minus minus 1. And this is just this prefactor, that's the induced metric times the Z from the normal derivative. Then there is a mixed term where on one side I have a B and the other side an A and the other way around. So one time I take a derivative with respect to Z to the power delta minus, and the other time I take a derivative with respect to Z to the delta plus. And that's this term. And then there are other terms, and all those other terms, right, they have positive powers of Z because they're delta plus and delta plus. And so I can ignore them. So near the boundary, and just to make sure that I do everything rather carefully, what I've done is I've not immediately taken the boundary value where z is 0, but I first put it at a small value epsilon, just to be careful. And then at the end of the day, I'm going to take epsilon to 0. And there's a very good reason why I had to do that, because if I naively would substitute in z is 0 here, again, I have this point that delta minus is generically a very negative number, right, for math. And this term would be diverge because it's z to some negative power. So I have to be more careful, and I have to first consider it at some epsilon away and think about how I'm going to deal with this divergence. This one we'll consider later, but let's first just consider this one. I mean, one step at a time. Okay. Now we should also realize, and this we do know from classical mechanics and from ordinary quantum field theory, that adding a boundary term to the action does not change the equation of motion. The flip side is that if I only know the equations of motion of my theory, the corresponding action is only fixed up to a boundary term. So I can always add for free other boundary terms, and my dominant dynamics will not change. So I'm going to make use of that freedom here. I'm going to say this is a nasty derivative, a nasty divergent term, but I have this freedom to add boundary terms by hand because my bulk equation of motion never knows about it. And I'm simply going to remove this from my system. Okay, and I can do that at the mathematical level very simply by adding this term, which is reverse engineered to make sure that this term is precisely the one that cancels this. And of course, I don't want any derivatives here because that would relate it back to the previous boundary term. I want to have, of course, a different type of boundary term. So if I add this particular term, which also has a subleading term of this type, right, then that precisely kills this most divergent term. Okay. Now I've just done this mathematically, but this is the reason why I briefly first introduced this notion of UVIR correspondence in the first part of the lecture. Because remember what you have to do in an ordinary quantum field theory. In an ordinary quantum field theory, we know there are UV divergences in the theory generically. And you know how, we also know very well how to deal with them. You have to regularize the theory, introduce a counter term that can absorb the regularization, and then you can have a finite answer where you still need to impose renormalization conditions to get the correct finite answer. But by the UVIR correspondence in ADS-CFT, the region Z is very small near the boundary, is precisely the UV of the CFT. So in CFT language, what I'm doing is nothing more than considering its deep UV, very high energy values, where I know there's divergence, but I know I should just add a counter term, right? And then carefully, right, adjust the counter term in the right way and remove it. So this precise procedure where you add a boundary counter term to the system to remove this divergence has been called holographic normalization or holographic normal ordering, in precisely because it is precisely analogous. And if you go into a little bit more detail and actually look at what happens to the correlation functions, if you could compute them at finite epsilon, it is precisely regulating the short distance singularity that you have in quantum field theory and adding the counter term to absorb it. Okay. In this particular case, it turns out that this very naive procedure also includes the correct renormalization conditions. You get the right answer, and so I will not discuss that in detail. But now I therefore, by the usual way of renormalization, the full action, the full quantum action, is the combination of the first term plus the counter term. That's the one that is fine. And now if I look at the following combination, if I add these two, I have the first term here, the first term here, this delta minus plus delta plus. If you work this out, delta minus is d over 2 minus this square root term. Delta plus is d over 2 plus this square root term. So in the sum, the square root cancels, and you just get 2 times d over 2. So that's d. This is just this term inherited. And here you see this delta minus term, that's from this cross term inherited. And remember, delta plus delta minus was precisely equal to d. So this is z to the power d. There was a z to the power minus d. That was the part from the induced metric. And now you see that precisely the powers of z all cancel out, and I can take my regulator to 0. Everything is now finite. Okay, but this then is the action compared to which I should take functional derivatives. This is now the action that I should consider as the generating function of correlation functions in the CFT. Okay, so let's now do that. Here I've simply restated this equation to make sure that on one slide we can see all the steps that we need to do. Now we're here. Now we use the GKPW rule and we say that e to the minus s, this total action, is the generating function of the correlation functions in the CFT, where I have to equate the value of phi at the boundary of AS with the source J. So to compute O, which is dd J in Fourier transform language is minus omega minus k. This is the definition of the 1-point function of this operator. Now I use the GKPW rule. I replaced this by e to the minus the action. Strictly speaking, I should have used here the path integral. But remember, we're computing the leading approximation. So I substitute not the path integral, but its on-shell value, but still subject to the correct boundary values. That the value of phi at the boundary, right, which by mathematical construction is A, but that by the GKPW rule should be equated to G. So whereas J here, I just write an A. Okay? And so this is the object that I have to take. Well, that is now very easy. Once you compute this, you get a D minus 2 delta minus minus times B. All the Z to the minus D's cancel, right? Strictly speaking, you have to, you also have a delta function over the frequency and momenta. So this integral drops away. And you have to be slightly careful with a factor of 2 that I'll explain in a moment. Okay? And here we have done our first ADS-CFT computation. Okay? We have computed the 1-point function of the operator in the presence of a source J. Okay? And we see here that equating the leading near boundaries behavior with the source, we already learned something. It implies that the response, right, is the subleading boundary behavior B. And this was one of these entries in the dictionary that I already sort of gave as a part of the ADS-CFT correspondence. But as part of the ADS-CFT correspondence that was implicit in the GKPW rule, but you can show how it follows from the GKPW rule. It follows that the subleading near boundary behavior is the corresponding response. And with subleading is really meant the independent solution to the other independent solution to the equations, second order differential equation that determines the fluctuations for phi. Are there any questions at this point?
Oh yeah, I have a question.
Yes.
Thank you for your explanation. I can't understand about why the interaction should be not diverging boundary at the boundary. Why it should be not diverging in the boundary? I can't understand.
I'm not sure I understand. I mean, it naively is divergent, right? And of course,
yes, I think we add the counter term action to remove the divergence divergence of interaction.
yes.
So I have a question about why it is the problem of the divergence of the interaction at the boundary.
Okay, I'm not sure I fully understand the question, but there are two things. One is simply if you would naively compute. In other words, you close your eyes and just compute. That's what I've done here. You find out that it's divergent in general. So you're basically forced to deal with it. And of course, at the same time, you know that you're computing some physical correlation function or some physical response. And like I said, these CFTs, you can measure them in second order phase transitions, and you get a beautiful finite answer. Your experimental colleague will not have to worry about this, right? So something in your theoretical computation goes wrong here, or in a slightly kinder way of phrasing it, you've been too naive where you just substitute this in blindly, right? You have to be more careful. And the way I presented it here is I simply was sort of, let's call it a down-to-earth physicist. The first thing a physicist does when he encounters an infinity is to regulate it and figure out a way to maneuver around it by introducing counter terms or whatever that. Or another classic way to deal with it is to compute relative objects rather than absolute objects. But what I also tried to explain, and in this particular case, we actually really at the physics level understand what we're doing here. And that's what I mentioned, that's why the UVIR correspondence that I started this lecture with is important, because we're really realizing that even though this is a divergence at z is 0 near the boundary of ADS, that precisely corresponds to studying the short distance behavior in the CFT, or in other words, the UV behavior. And we know that field theories, ordinary field theories, even conformal field theories, if you compute them naively, will have divergences, right? And you have to add counter terms in these systems to compute them. The special part about a conformal field theory is that, of course, this counter term, once you do it and you do it in the right way, turns out to be trivial because you have no running RG flow. The dependence on the RG scale will, at the end of the day, drop out. But if I give you let's say n equals 4 super Yang-Mills theory, which I secretly know is a conformal field theory, but you just follow a textbook computation of Yang-Mills theory, it will look like you will encounter all these infinities all along. It's only when you sum up all the Feynman diagrams at the end of the day that you realize that the infinity drops out. Okay.
Thank you so much.
Yeah, so it's the same here. So rather, there is you can construct a super special way that at the end of the day, and people know how to do this also in conformal field theory, that you don't encounter this infinity. That has to do with some very special features. Here, actually, the crucial feature is that you have the operator has to be a marginal operator, and that's precisely the operator where delta minus is 0. As you see, if delta minus is 0, you don't need a counter term. Okay.
Yes,
whereas if delta minus is not 0, you've actually secretly deformed the CFT and thereby introduced the scale, and then the divergence reappears.
That's right.
Okay.
Thank you. Yes, thank you.
You're welcome.
Thank you so
This is very important. So that's very good that you asked these questions. Okay. So we've now completed. Yeah, further questions. Yes, please.
Oh, yeah. So at the boundary, we have two mode, A and B. And
yes,
can you say something about boundary condition? For example, Dirichlet or Neumann condition, depending on the condition, we have to fix one of them. The other is free to fluctuate. So can you?
Very good.
Also,
I will use that right now in computing not the 1-point function, but the 2-point function. So I'm going to ask you to hold your question, and I'm going to explain it. And if you still have a question then, or at some moment want to interrupt me with a question, please do, because you again raise a super crucial point that's going to come up right now.
Oh yeah, thank you.
In fact, you see it on the next slide. Okay. So if there are no further questions about the 1-point function, let's now be a little bit more ambitious, and we're now going to compute the 2-point function. Okay, for that you need to take one more derivative with respect to the source. right? And then you can put the source, in fact, equal to 0. Now, to do this, you need to be a little bit more careful. I was rather quick with the 1-point function because it's rather easy. Strictly speaking, what you're doing is you're solving a Dirichlet boundary value problem. Remember that the GKPW condition tells you that the value of phi at the boundary should be equal to the source. That means in terms of the calculus of variations, that it does not fluctuate, precisely like the question stated before. So if that value does not fluctuate, right, that means that the fluctuation at the boundary is 0, and that's called a Dirichlet problem. Okay, and we will see it right now in some more detail. So Dirichlet and Neumann problems you know from electrostatics and electrodynamics. So let's take a small step back towards our electrostatics, and again to the theory of differential equations, and in particular, how do I solve a Dirichlet problem in these theory of differential equations. So the equation of motion for phi, as we saw, has 2 independent solutions, and strictly speaking, the Dirichlet solution, as I said, that's the solution where the boundary value does not fluctuate. So that has to be the solution where A is 0, right? Because remember, the solution where A is finite has support at the boundary. In fact, for generic D minus, it actually blows up near Z is 0. But the solution where A is 0, in other words, only has support B, beautifully goes to 0 as the boundary because its exponent is positive. So the only fluctuating degree, the correct fluctuating degree, is phi B, where B is non-zero, right? Which behaves in general as B to the power Z plus, and then higher order powers in Z. Okay? Now to solve the system, we will still need that other solution, right? But in terms of the Dirichlet problem, again, this must be the solution whose other boundary value is determined by the interior. Okay, and now we see that in a more detail. I already described it a little bit earlier, but in the 1-point function, you didn't actually see it back where B was determined. And now we are going to see back how B is determined in more detail. So let's denote phi interior of Z as the other solution, as another independent solution. It's not orthogonal to phi B. It's just another solution, but a solution whose boundary determined by regularity in the interior of ADS. And in terms of this Dirichlet problem, where you have boundary conditions on both sides, that's why I emphasized in the beginning, right? You now know how to construct the Green's function. Okay? Now, this Green's function must obey the correct boundary conditions. So in particular, as Z goes to 0, the Green's function describes what the fluctuating fields does, not what the background field does. So since the fluctuating field vanishes at the boundary, the Green's function must vanish at the boundary, must vanish at Z is 0. And the ordinary way you construct the Green's function is you take 2 solutions to the equations of motion, right? And you multiply them by a theta function, and then you take the opposite order and multiply them by the opposite theta function. Because then if you act with the second order differential equation on this, the theta function will make it into a delta function, and then the remaining parts act precisely on these 2 solutions to be 0, and then you just have to normalize the delta function in the right way. Since one of the derivatives acts on the delta function, you get this combination at the bottom, which acts like this. And of course, the other solution, look, here's this theta Z minus Z prime, right? So if now I have to do this, I hope I did this correctly. If Z is very, very small, I think I just did it. I think my notation here is just wrong. So this is one of the things I'll have to correct. If Z is very, very small, then I have here, we have here theta. This is then a negative number. So that seems to be incorrect. This should be a positive number, right? And then you see that this is phi B of Z, phi integer of Z prime. So as Z goes to 0, this dominates and indeed it vanishes. Okay. and here the other way around. So let me make a small note to myself. I will adjust these slides and send you an updated version after the lecture. Okay. Now, as you also may remember from your theory of differential equations, that this particular combination, and especially in electrostatics is important, this combination is called the Wronskian, right? It has several functions. First of all, the simplest one is that it gives you the correct normalization for the Green's function, right? That the Green's function, that the operator acting on the Green's function gives you a delta function, okay? It also is another object. It is also the object that tells you whether these two solutions are independent or not. If the Wronskian is non-zero, then these are two independent solutions. So it's a measure of orthogonality of these two solutions, right? And then the third thing that's important, if in terms of electrostatics, it also measures the flux through a surface A. And that last part will come back tomorrow. Now, if you normalize this correctly, this Wronskian is also independent of the location where you measure at C, because it's just a measure of orthogonality, and things are orthogonal or not. So they're either non-zero or they're zero. And this Wronskian will play an important role later. Okay. Now, remember, we're using a Dirichlet problem. So since the Green's function itself vanishes at the boundary Z0, you now have to ask yourself, how do you evolve a boundary source where you have a boundary value Z with the Green's function to find the appropriate field value at an arbitrary point away? And this is explained by Green's theorem, which you may review in your electrostatics theorem. And the solution that if you want to know the field value at an arbitrary value of Z, given a boundary source J omega K, where I've already sort of in a preview towards applying this CFT called the boundary source J, you should not convolve it with the Green's function itself, but the derivative of the Green's function near the boundary, and then take the limit where you take the value at the boundary, right? So in order for this derivative, it's very well known that you first compute the derivative with respect to the argument and then send it to infinity. If you would do the other way around, it becomes ambiguous. And now we know what the general expression is for this Green's function, so we can just substitute it in. We can just take this derivative and substitute it in. Now, clearly, when this derivative acts on the phi interior part, well, I mean, the theta function already does it for you, but if it would act on the phi interior part, then taking phi beta to 0 would give 0. So this acts precisely on the phi beta, you get the derivative of phi b at the boundary times phi interior at Z. So the theta function controls that it's this combination that survives, and it's precisely now the derivatives appears of phi b and not phi b itself, because phi b itself would vanish at the boundary. Okay. And then Green's theorem tells you that this precisely convolves to give you, once you have a source on the boundary, how the electrostatic potential looks like in the bulk. Okay. Moreover, you can also see that by construction, it obeys now the right boundary condition. In fact, that's part of the derivation of Green's theorem. If I take Z to 0, now also take Z to 0, then you get a Z0 here. But remember, I can evaluate this Wronskian at any point Z. So let me evaluate the Wronskian also at the point Z is 0. Then I can ignore this second term, and this just becomes phi integer defined boundary Z. These, then once this is at the same point epsilon, these cancel, this is 1, and you just get J back. Okay. If you don't immediately see it from this slide, it is it's a 2-line exercise, good for you to recall how the Dirichlet Green's functions work. So that's by construction. Okay. Now, what we want to do, remember, is we have to construct the on-shell action We have to construct a solution to the equations of motion given the appropriate boundary conditions and substitute that into the action. This is that solution that we have to substitute back into the action. Remember, this is phi sol given the appropriate boundary condition J. And remember the boundary action, because the bulk action vanished on shell, the boundary action consisted of two terms. We needed phi sol, but we also needed the derivative with respect to z of phi sol. So let's compute that. That means that substituting in using the Dirichlet-Green's function, I now have to take not just the z prime derivative, but also the dz derivative. Okay, and that is this particular combination. And now again, I evaluate the Wronskian at the particular point where phi near the boundary where phi b vanishes. So the Wronskian is actually only proportional to phi integer times the derivative phi b. And then you see that the phi b term, the derivative of phi b cancels for this particular term. And so the derivative is just this combination right here. Does everybody see this? Okay. Because now we have the two ingredients. We know that phi near the boundary just becomes j, and the derivative phi near the just becomes this ratio of d phi integer at the arbitrary point z divided by phi whose boundary condition is set by the interior at the regulating value epsilon. Now we're going to substitute both these into the action. Now remember, I still needed this counter term. That does not change. Okay, that was the point of computing this 1-point function. So the actual boundary action that I need to quote is this combination. I have the term that I got from my integration by parts, phi solution times the derivative phi solution. This was from the induced metric. And I have this counter term, which is z to the minus d just phi sol squared. And now I'm going to substitute in the value for phi sol computed with the Dirichlet-Green's function. Now phi sol itself is just j. dz phi sol was the derivative of phi integer at the point z divided by phi whose boundary condition was set by the interior at the point epsilon. But remember, I now have to take all this at the boundary value. So everywhere there was a z here, I may now freely substitute in epsilon. So I get, at the end of the day, I get that this is the derivative of the phi whose boundary conditions are set by the interior at epsilon divided by phi whose boundary conditions are set by the interior at epsilon. And then the second term is just phi sol squared. So that's actually easy. This is just j with an epsilon to the minus d. Okay. Now we do have to do one more step. And this is the final step to compute this. Remember that the generic solution to the second order differential equation was something like a z to the delta minus plus b z to the delta plus. And to construct the Green's function, we needed two solutions. We needed the Dirichlet part, the part where a is 0, that we called phi b. That was to enforce the correct boundary conditions at the boundary. And then there was another part, this phi whose boundary conditions set by the interior, whose boundary conditions were set by the interior. But at the boundary, at the other end, it still must decompose into an A part and a B part. Okay? Right? Those are the two independent solutions. All right? So I know that near the boundary, which is where I had this still has this following behavior. But where now A int and B int are two objects that are set by the boundary conditions at the interior. Okay. Now I am fully ready. Now I can compute O, the 2-point function, because I just take two functional derivatives with respect to the sources J. Right? That's very easy, right? I have the two J's and I just essentially I can just drop them and I get the following parts. I get this epsilon to the d plus 1 minus d plus 1 part. I get this part, d phi interior divided by phi interior. And then I get this part that was controlled the divergence. in the system. Okay. Now, it takes a moment to realize that actually you can write this term in a very simple way. You can put this delta minus inside in the following way. Right? If I would now compute the epsilon of this, right, it either can act on phi interior, then the prefactor cancels and I get this, or I can act on the epsilon of minus delta minus, then I get a minus delta minus, but then the phi interior cancels out. This is not a coincidence, because now look what this means. Now I have to evaluate this at the boundary. If I look at the bottom part, this is epsilon to the minus delta minus times phi interior, that precisely when z is epsilon makes this exponent 0, and this a positive exponent. So if I take it to the boundary, this term vanishes and I'm only left with a right here. But it's more important what happens to the derivative. Again, this derivative makes this a constant, this a positive power, right? But now I have to take the derivative. I have to take the derivative with something that doesn't depend on z. So that term cancels or vanishes. And then actually the derivative just precisely picks up this second point term with a prefactor by acting on this d plus minus delta minus, right? And if you trace very carefully the powers of epsilon, you get the following combination out. Okay, it looks like you still have a divergence here, right? Whereas we've just argued, and including the question that was a moment ago, that we should have a finite answer. Okay, now if you are very careful, right, you actually have to renormalize these sources precisely. See, there's precisely a power of 2. So if I renormalize each source by absorbing an extra power of epsilon, I can get rid of it, right? This is also something that if you work very carefully in quantum field theory and you want to extract the S matrix, right, you also have to do a renormalization of the sources in this way. But we all know how it happens, works for the S matrices in quantum field theory. At the end of the day, you basically drop the external legs of all your Feynman diagrams and you just put the on-shell condition. Here, it's very similar, even though technically there's an extremely involved step with renormalizing sources. The end result of that technical issue is that you just drop overall divergence and you're done. Okay? And so you just drop this and you precisely get the following object. You get d minus 2 delta minus, that was the factor before, times b divided by a. And if you think in terms of linear response, what a 2-point function is, right? Once a 2-point function is linear response, you perturb the field a little bit and you look like the response. So that means that if the perturbation is linear in the source of the perturbation itself, and then the linear response answer, or the Green's function, precisely divides out that normalization. So b divided by a is precisely the expectation that you would get if a is the source of a linear response 2-point function. Are there any questions at this point? Okay. Well, this was basically I see that I'm slightly gearing my lectures to be a little bit shorter than planned. I'll do my best to compensate for that tomorrow and make them a little bit more ambitious, because this is what I wanted to tell you today. I've really explained to you or if I've taken you step by step through computation of Green's function in ADS CFT. And we will compute one more Green's function in quite some detail. But as I go along in the lecture, I will more and more sort of give you the answer. And this is the way you compute them. And sort of as an exercise, I've written down here a problem where you do the same thing, not for an scalar operator, but for a vector operator. Are there any questions at this moment?
Oh, I have a question.
Sure.
So will you also give me a talk about computing higher point function, or any comment about it?
No, but since you've asked, to do it here off the top of my head, or sort of without unprepared slides, if I had a blackboard, I could do it, but I don't. But I can start next tomorrow with some comments about how to compute higher point functions.
Oh, okay, thanks.
Okay, but the essence is very similar to what you what I have here. Okay, so I will do that. I will show you how to compute a 3-point function.
Oh, thank you.
Any further questions?
So far, you've discussed everything analytically. What would you do if you were doing this numerically?
So if you would do this numerically, that's a very good question. You have this general expression for, say, a 2-point function. A 3-point function is more involved, but a 2-point function, which is just this B. So this is the solution, right, to the field, to the equation of motion, right, where the boundary conditions are fixed in the interior. If you look carefully, there should be the subscript int here. So numerically, I simply solve the equation of motion in ADS with the boundary conditions imposed by the interior, and then there's an overall value at the boundary which I don't worry about, right? Because I'm going to divide it out, and then I simply compute what numerically what B int and A int are, and I literally take the ratio.
Okay, thank you. Do you typically in the numerical calculation have to regularize out infinities, divergence?
Yes, you actually numerically you precisely have to, because to find out what these A interior and B interior are is, right? You often use a trick like this. You simply you solve this numerically, right? And then you extract the leading behavior near some Z large, but you can never take Z small near the boundary. You can never take Z as 0 infinity, because then numerically you blow up, right? So you carefully try to extrapolate this. And for B interior, the same thing is you try to take a derivative with this correct prefactor such that it vanishes, and then you extract it out.
Okay, thank you very
numerically,
much.
you have to very carefully regularize towards the boundary to get this, to get these coefficients exactly. Yes.
Okay, great. Great.
Any further questions?
Oh, I have one more very nice
Yes.
question. So you mentioned what to say. So is there any ambiguity about determining the counter term? Because naively, I guess if I use if there is possible another counter term, then the result of this 2-point function might different. So
Yes,
I just
so
want
I glossed it over, but you're totally correct. Well, I didn't gloss it over. I mentioned it, but I didn't tell you the story that when you add counter terms also in quantum field theory, and like I said, this is literally one-to-one a mathematical translation of the normal renormalization in quantum field theory. So you add a counter term to remove the divergence, but strictly speaking, you have then infinity minus infinity, and you have to have a finite remainder. And of course, if you don't subtract the infinity in the right way, you can get any finite remainder that you want, right? So the way you often do that is you impose what's called a renormalization condition, right? Which means you use one measurement, or you use one value of omega and k in a Green's function, usually the values where omega is 0 or omega and k is 0 to fix this ambiguity. And then for other values of omega and k, it is determined. So secretly here, I know that aside from this term, right, if I use this boundary regularization, I don't need a further counter term, a finite part.
Mhm.
Okay.
Oh, okay, thank you.
Yeah, but it's indeed a subtlety, and this is a, so it in the same way that quantum field theory renormalization has a whole field, there's sort of a small subfield of what's called holographic renormalization to do this.
Okay,
Yeah.
thank you for your answer.
You're welcome. Good. If there are no further questions, also here I have a small, like I said, a small exercise, something to try out. As I said, there in the slides that Kyung has put on the school website, so you can download them there. For tomorrow, what I'll start with the higher point function as the request, and if people have questions about these exercises, I can also answer them. And I'm in Europe, so I'm a few hours behind you. That also means that if in the evening you have a question about this, feel free to write me an email, because I'm still awake and I can answer it. If there are no further questions, then thank you so much for your attention.
Great. So thank you for a very nice talk. Let me check again. Can you have any other questions or comments from the audience? No?
I have one question. Maybe.
Sure.
Yes.
About this I mean the dropping factor epsilon to the some power. So if you evaluated initial action in the previous page,
Yes.
maybe few, right, and that was completely finite, right? No, before. When before you evaluate the 1 point function, yes, in 4
Yes.
point.
This one is finite, yes.
Yes, right. And if you define 2 point function of O as a second derivative of, I mean, the initial action, which is finite, and you identify J and A, then I wonder what is the source of that infinity?
Well, okay, so this factor of 2 is also related.
I don't
to that.
care that is a
Yeah, but it's important because it's related to the fact that this is the O in the presence of J.
I know, right?
But the correct way, the correct identification of, and that's the subtlety, is that this identification of A is equal to J is strictly speaking not correct. It's
probably
A should be equal to E to the delta minus J, epsilon to the delta minus J. Or J is epsilon to the delta minus A.
I see.
And then,
I see.
and you can also see that actually for the 3-point function, which I didn't discuss here. You will get, if you get a 3-point function, you will get here epsilon to the 3 delta minus.
So probably what you did is you are taking the derivative of the just the first part,
Yes, exactly.
not the just the A.
Yeah, exactly.
That's the source of that.
Yes.
Right. But right. But if you just naively just take the its definition as the derivative with respect to A, then maybe that is just equally good, probably.
So yeah, so that's what I said. In the end, at the end of the day, you can often, in the same way that in quantum, it's literally the same as a quantum field theory. And
I think that now it's pretty clear.
That if you you also have this very careful Cullen-Lehmann LSZ reduction of the sources, which includes a renormalization factor if you do this at loop order. Right. But at the end of the day, what you always do if you compute on-shell S matrix elements, you just drop all those dependencies, and it's the same here. And that's why at the end of the day, often just taking the derivative with respect to A is fine, as long as you ignore the last remaining epsilons.
Yes, right. So if you are taking the derivative with respect to leading piece, then you always have to drop that.
Yeah,
piece,
yeah,
right?
yeah.
While if you take the derivative with respect to A, and
exactly,
that you don't need.
Yeah, yeah.
Anyway, it's very clear.
Yeah.
I wonder if you can say something about the divergence of the other solution in the interior. So phi int is a regular solution in the interior, but the other linearly independent solution must be singular.
So in pure ADS, like the situation that we have here, that has no meaning. Because that has a you can show that has a singularity at.
But if you take into account the bang reaction, at the end of the day, I mean, the system is.
It's not the back reaction, but if you take not pure ADS, but let's say an ADS black hole, which we'll do later, or other situations where the ADS has some structure in the interior, you will actually see that both solutions have meaning, and they're easily extracted. For instance, we will see tomorrow that the two solutions correspond to, one computes the advanced Green's function and the other computes the retarded Green's function. So the best way to think about what the boundary condition in the interior does, it tells you the type of Green's function that you compute. Right, so you know that if you compute things in flat Minkowski space, the difference between advanced, retarded, forward, lesser, greater, and Feynman are marginal. At the moment you do this at finite temperature or a finite density, they become really different Green's functions, it's easier to understand, oddly enough, in a situation where you don't have pure ADS than pure ADS.
Okay, so you mentioned the difference coming from different gravity backgrounds like black hole and so on. But I guess there can be huge difference coming from the self-interaction of the scalar field, for
instance. You mean to the correction to the boundary conditions in the interior from the self-interaction of the scalar field?
I guess, the near boundary behavior is completely determined by the quadratic part of the scalar field, but the IR behavior should depend on higher terms if you consider series expansion of the scalar potential.
That is, yes, I think I understand what you're saying, but you will not see it in the intermediate calculations. What you will absolutely see is that if you compute the 3-point function or higher point functions, this actually is a good point. Let me phrase it differently. If you compute the 3 or the 4-point functions of a scalar operator in ADS, and you look at the final result, and you now look at the infrared behavior of the system, right? So low frequency or large momenta, you will clearly see if this is a relevant interaction that it contributes strongly. That's your point,
Yeah.
right?
Yeah.
But interestingly enough, if you look in the ADS computation, nothing special will happen at the specific point z is 0. Z is infinity. Sorry, at this, right? You can smoothly integrate over that point. And in fact, what I'll show tomorrow when I discuss a higher point function, you actually have to just integrate over all possible points where there's an interaction vertex. And precisely because the fluctuation value of phi does not diverge at z is infinity, there's nothing goes wrong in that calculation. And what this shows you is something that's very important that I think is something that I always emphasize, but is often forgotten, is that this UVIR correspondence that I started this lecture with, that is not an exact science. It is not literally so that if I compute things at z is 10, that this corresponds immediately one-on-one to the CFT scale IR. You have to think of it as a little bit more a qualitative sense, in the sense that the IR physics is dominated by what happens in the interior, but it's not one-on-one. So what you can show is that indeed the fact that if you have a relevant operator and the fact that the 3-point function contributes mostly in the IR is related to the fact that the dominant support of this integral will be from the interior of ADS. So in that sense, the UVIR correspondence works. But it's not true that the specific point z is infinity, which is the deep interior, right, is the one that completely controls the IR behavior of the Green's function. I hope that some way answers your question. I can give other examples where the naive UVIR correspondence does not work, right? So you have to take it as a qualitative guideline, but you cannot take it as an exact mathematical equivalence.
Another question I would like to also raise is whether, I mean, this computation, obviously you have been using Poincare patch of the ADS. If you switch to global patch, I mean, there might be some, I don't know, non-trivial change, some subtlety.
There are not so many subtleties. It's mathematically more tricky for two reasons. Well, they're all related reasons. In global ADS, the boundary is now a sphere. So the natural, so to say, Fourier coordinates are spherical harmonics. And for a 2-point function, that's still no issue. But for a 3-point function, that becomes kind of messy, right? You need this overlap of 3 spherical harmonics. And on the other side, you have a discrete spectrum that makes it a little bit easier. But the radial dynamics that I describe here are essentially the same.
Okay, thanks.
Good. Any further questions?
I have another question.
Sure.
Yep, sure.
So is this binary expression could be differ by including some interaction term, or
Which expression?
So
the
this
2-point function?
2-point function, yeah, proportional to
Yeah,
something over.
this is you're totally right. This is exactly like in quantum field theory. This is the leading contribution to the 2-point function, right? In the same way in quantum field theory, you can compute the sort of the self-energy corrections to the 2-point function. It's the same here.
I mean the B over A, this expression can be differ by including some interaction term
No,
in
the
the
B
gravitational field.
the B over A term stays, but there is a whole other term, which is a much more complicated function of B, A, and whatever. That and there's a very easy way to see that it has to be a much more complicated term that you add. You know that if you in a self-energy term, right, you have to integrate over loops, and there's a relative momentum where you have to integrate over, right? Whereas here you see explicitly that there's only one momenta that appears in the expression.
Mm-hmm.
So this is literally like, you know, in terms of Feynman diagrams, this is a straight line. Right? And actually the diagram that I will show you tomorrow shows you precisely that there's something like a Feynman diagram expansion in ADS as well. And there is indeed a loop. There's a loop contribution, roughly speaking, to this object, which is difficult to compute because you have to compute a loop in gravity, but in principle, it's possible.
Mm-hmm. Thank you.
But I guess that if you are talking about the polynomial type interaction term, that would not change the B of A. Maybe it changed the B, but it wouldn't change the general expression B of A, because the whole holographically renormalized interaction should be just the boundary term, right? It's coming just from the kinetic term.
Yeah, there is a way. I think what you say is there is a way to recast it again at the end of the day as a B over A term.
Yes,
that's correct.
Right.
Yeah. Yes, that's correct. If I think of B and A, yeah, no, that's you're correct. Yeah.
Okay,
good.
I think we do not have more questions or comments. So we can just stop here for today.
Yeah.
Oh,
great. Thank you very much.
Let's thank.
Very
thank you.
Lecture.
Well, thank you for your attention, and I look forward to tomorrow.